guys? Today we're going to be doing a video on optimization. Optimization is effectively an application of differentiation. It's pretty similar to related rates, but it's actually quite different in some ways. Let's get started. So in optimization, what we're trying to do is that we're trying to maximize a quantity in terms of something. By obtaining a particular value of something, you're effectively maximizing the quantity or minimizing the quantity. In other words, to just say is optimizing the quantity. So a typical example is optimizing length in terms of theta. So you'd find an expression that represents the length in terms of theta. And what you would do is that you'd find the value of theta, which optimizes the length. And this is where the notion of differentiation comes in the sense that when you find the expression, you'd find its first derivative, and then you set, because you want to find a maximum or minimum, a maximum or minimum on an f at x graph is effectively the roots in an f prime of x graph. And so you'd need to set that equal to 0 to find the roots, and thus you find the optimum values. To give a framework of how optimization problem works, you effectively find an expression in terms of what you want, and then you find the optimum via the derivative. Here's a IB question, paper 1, no calculator. It states that a packaging company makes boxes for chocolates. An example of a box is shown below. This box is closed and the top and bottom of the box are identical regular hexagons of side axiom. So x there. Part A. Show that the area of each hexagon is 3 root 3x squared over 2 cm squared. Part B. Given that the volume of the box is 90 cm squared, show that when x is equal to cube root of 20, the total surface area of the box is a minimum, justifying that this value gives a minimum. I'll give you 5 seconds to just process the question. So hopefully the question makes sense and is not overly difficult. Let's point out some key pointers in what the question is trying to ask. So they mentioned that the box is closed, so effectively there's a lid on the box, and what that means is that you would consider the top when calculating some value, aka the surface area in this case, and the fact that the bottom and the top are identical regular hexagons. Keep in mind they mentioned regular, and they're nice that they've shown somewhat of a skeletal diagram of what a hexagon looks like, in which there are 6 triangles. Now, these questions in optimization, you can recognize an optimization question by, as you looked at part A and part B, they mentioned that the total surface area of the box is a minimum. Anytime you see minimum or maximum, very good chance, almost 99% chance it's relating to optimization, which is a good thing because you know now what the question, like which area of the topic the question relates to. And it's different to related rates because in related rates they will ask you find the value at this particular moment, and it's relative and it's relevant to time, and it's more relevant to time. Whereas optimization, yeah, there are a few questions that relate to time, but most of them don't relate to time. So this is a common framework in the optimization questions is that they'll ask you to derive an expression, and you'd often have to show it. So that is helpful because you know that, because in optimization you need to find an expression in terms of something, and so they'll help. So that's your part A, and then your part B was finding the actual optimum value, or finding the value that optimizes something, and that you essentially get number 2 by connecting part 1's expression to the extra step in part 2 is effectively differentiating, setting to 0, and justifying or checking whether it actually corresponds to the minimum maximum by doing either the second derivative test or checking values left and right to your root. So for part A, they are asking you to find or show that the area of each hexagon is 3 root 3 x squared over 2 cm squared. Now the biggest hint is that a hexagon consists of 6 equilateral triangles. And in this case, the 3 sides are x centimeters, and each of the angles are 60 degrees. Now, the area of a hexagon consists of 6 triangles, and so by finding the area of the 6 triangles, we can, let me rephrase that one more time. So the area of the hexagon consists of 6 triangles. each of the 6 triangles has an area that can be represented by the half AB sine C formula, in which A and B are represented by x and x, and C, which is the angle between the two sides, is 60 degrees, or pi over 3. So we need to multiply that quantity by 6. So 6 times half times x times sine 60. We can simplify 6 times half, cancel out the 6 and 2's. Sorry, get a factor. So 3 times x sine 60. Sine 60 is root 3 over 2. A common trick is you can see that the question, like as you're solving it, you can see that you're noticing some of the parts are matching. Because notice here, sine 60, root 3 over 2, root 3 over 2. X squared, and then the 3 as well. So that definitely means that you're on the right track. And so you justify that the area of the hexagon is 3 root 3 over 2 x squared cm squared. Now, part B. Given that the volume of the box is 90 centimeter cubed, you have to show that when x, so this length, is equivalent to the cube root of 20, this total surface area of the box is a minimum. So this is a classic optimization problem, because what they've given you, before that, you have to consider that when you find the surface area of the box, you need to consider the h value, the height of the rectangle, right? Because it consists of 6 rectangles and 2 hexagons, and you need the height of the rectangle. Now, you can't straight up say, oh, it's h, because when you try to differentiate with respect to x, you're gonna have to just write it as dh by dx instead of an actual quantity. So that's why they've given you the volume of the prism, because what that is that it's a constraint equation. So you've been given that the volume of the prism is 90 centimeters cubed. And I'm just reiterating what we need to do. We want to find the length that minimizes surface area, which in this case, x is equivalent to the cube root of 20. And we need to express the equation in terms of one variable. So that's the approach. Hint, in this case, it was x, which is why they asked you to find, which is why you notice in part A, they had the variable x in it. So the volume of a prism is 90, and it can be represented by the area of the base times its height. What we want to do is express the height in terms of x, because when we differentiate in that surface area equation, we can quickly find the derivative instead of implicitly differentiating it. So we isolate. So h is equal to 90 times 2 over 3 root 3 x squared. Notice the x squared goes to the bottom, not remaining on the top. So we can simplify this. So in this case, how was it done? So in this case, 90 and 3 becomes 30. 30 times 2 is 60. 60 over root 3 x squared centimeters. Now, the equation for a surface area of a prism can be represented by the area of the 6 rectangles, so 1, 2, 3, 4, 5, 6, and the area of 2 hexagons, one at the top, one on the bottom. And I've drawn the diagrams here. So x, 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 and h. So it's 6 of these, 6 rectangles and 2 hexagons. Notice that for the rectangles, this is the area of the base times the height. So x times the height, which we found, 60 over root 3x squared. And for the hexagons, our expression was 3 root 3 over 2. And because it's 2 of them, the 2 and the over 2 cancel out, so it becomes 3 root 3. So we've simplified, and this becomes 360 over root 3 times 1 over x plus 3 root 3 x squared. Now notice that I've written it like this because I want to make it easier for me to differentiate, because the derivative of 1 over x is negative 1 over x squared. So I've effectively squished out the coefficient, so that's just easier for me to recognize when differentiating. For something like 3 root 3x squared, it's pretty easy to notice, hence you don't need to do too much about it. And this expression here is effectively our surface area expression. We have everything. All we need to do now is to find the optimum surface area. And by doing so, we're going to differentiate the surface area with respect to x, find the derivative, set it to 0, and that gives us the optimum. And hopefully that gives us the cube root of 20. So that's what I'm saying. Optimize surface area based on x. Note, SA is surface area. So d of SA over d of x. So 360 over root 3 is just 360 over root 3. because it's with the 1 over x, right? The derivative of 1 over x is negative 1 over x squared. You have to, some of these you have to know. So something like root x is 1 over 2 root x. For 1 over x, it's negative 1 over x squared. You just have to know these because these ones often come up. To give you an analogy, it's something like knowing the cosine values, cos 30, cos 45, cos 60, sine 30 half, sine 45 root 2 over 2. It's like, this has to like be quick, because when you're doing paper 1, you have to be quick in solving these questions. So you have to be comfortable with just knowing these. And that just comes through a lot of practice, but also just being cognizant of what you're doing. So we differentiated. I differentiated this part, and the derivative of this is 3 root 3 times 2x. So 3 root 3 times 2, 6 root 3x. And now, finding maximum or minimum, in this case it was minimum, hence it's a 0 on the f prime of x, but it's actually a local minima on the f at x graph. So we set it to 0. So we moved the 360 over root 3 to the left. I moved it to the left because 6 root 3x is equal to 360 over root 3x squared. We're going to bring the x squared and the root 3 to the left by multiplying. So 6 root 3 times root 3x, 6 root 3 times x times root 3x squared is equal to 360. I apologize for my appalling writing here. So root 3 times root 3 is 3. X times x squared, x cubed. So 6 times 3x cubed is equal to 360. 18x cubed is equal to 360. Sorry, I made a mistake here. Not the neatest type of form. Hold on, give me 1 second. I made a mistake because you can see I wrote x is equal to 20, which is not what the answer, which is not what it's supposed to be. It's supposed to be x cubed. So x is equal to the cube root of 3, the cube root of 20. And so we've justified that to minimize the surface area, we found that the x value has to be the cube root of 20. Now to justify, because often what happens is that when you find a value, you'll be thinking, oh, is it the minimum or maximum? Because when you find a 0, yes, it's a 0 on the first derivative graph, but is it a minimum or is it a maximum on the actual f at x graph? Sorry, the original function. And this is where you can do you can use two approaches typically. And in these, and there's another one too, but it's the other one is based on the other one. Sorry for my gibberish there. So for the first one, you can leverage the second derivative test, and it's pretty useful, especially if the expression is very easy to find the second derivative. When it's not, though, the other option is to test some values on the left and the right of the value you found. And to add on to that, if you've been given a domain, you can quickly just analyze the endpoints and see how the function is behaving. So in this one, I'm going to use the second derivative test because recall that f prime of x is just negative 360 over root 3 times 1 over x squared plus 6 root 3x. This is very easy to differentiate because I know the derivative of 1 over x squared. So this becomes 7 over 20 over root 3 x to the negative 3 plus 6 root 3. And if you sub in 3 cube root 20 into x to the negative 3, you can just know it's more than 0. And also because the fact that they've given you the instruction you have to justify it's a minimum, you know that in the second derivative, if f prime of c is equal to 0, but the second derivative of c, so f double prime of c is more than 0, you know that c is the local minimum. So you can see here that it is more than 0 if you actually think about it, but there's a quick trick that you can just know and just say, yep, it's more than 0. So via substituting, and thus since f prime of cube root of 20 is equal to 0, and f double prime of cube root of 20 is more than 0, this supports that x is equal to the cube root of 20 is indeed a minimum. Hopefully that question was okay. This is typically the more, I guess, the slightly more easy ones in the sense that it's volume and surface area. So the trick is that they'll give you a constraint equation where you express the height or some quantity in terms of something like the radius or something like the length in this case, and then just differentiate with respect to that value. So let's do in this one. Hold on, sorry. Let's take a quick read of the question. It's saying that in triangle ABC, BC is equivalent to root 3, angle ABC is equal to theta, and angle BCA is equal to pi over 3. Part A is saying that show that the length AB is equal to 3 over root 3 cos theta plus sine theta. And part B, given that AB has a minimum value, determine the value of theta for which this occurs. I'll give you a quick 5 or 6 seconds to just process what's going on. By the way, this is paper 1, so no calculator. So, in any of these questions, especially geometry ones, you gotta be drawing a diagram. Like, it's just very useful. And we've drawn the diagram, so we've labeled ABC. So in this diagram, there are derived and the given quantities. So ABC, BC root 3, ABC theta, and BCA pi over 3. Now they're asking you to show that the length AB is equal to 3 over root 3 cos theta plus sine theta. They're asking you to find the AB length. Now, intuitively, you're probably thinking either something along the lines of cosine law or sine law to find the length, but you can't find cosine law because you don't know AC, although you know the angle in the middle, so that you could have easily found AB. But the other way is that BC is opposite to A, and pi over 3 is opposite to AB. So hence, you need to find an expression for angle A that will help you find the length AB. And we've done that here because the angle of all the angles in a triangle is pi, or 180 degrees. So angle BAC is equivalent to pi minus pi over 3 minus theta. So 2 pi over 3 minus theta. So now we're going to leverage sine law, in which BC, so the length over the angle opposite to it. So sine BAC is equivalent to AB over sine pi over 3. And we want to find AB. And BC is equivalent to root 3. And BAC is 2 pi over 3 minus theta. So I've substituted that in. Now we're going to isolate for AB by multiplying root 3 over 2 to the left. So root 3 times root 3 over 2 over sine 2 pi over 3 minus theta is equivalent to AB. You'll notice here that for sine 2 pi over 3 minus theta, initially you'd be thinking of using like the classic tricks where something like sine pi minus theta is theta via Cauchy rule. But in this one, it's not so straight cut. So I use the sine identities in which the sine A minus B identity. So it'd be, so I've simplified, root 3 times root 3 over 2, 3 over 2 over, sine 2 pi over 3 cos pi minus, we want to correspond that with a minus. These are formulas that you should know, and if worse push comes to shove, you'll quickly look at a data booklet of answers that are making sense, but you should know these formulas. Same goes to the cosine identities. Tangent is understandable because, let's be honest, no one likes tangent. And so minus sine theta times cos 2 pi over 3 is equal to AB. And again, this is where you need to know your angles. 2 pi over 3, 2 pi over 3, second quadrant. And sine is positive in the second quadrant, but cosine is negative in the second quadrant via Cauchy rule. So sine 2 pi over 3 is, so essentially it's sine pi over 3, which is sine 60, and so root 3 over 2. These are things that are going in your head, so you should be knowing this. Root 3 over 2 cos theta, you can't evaluate cos theta. So minus sine theta, so cos 2 pi over 3 is negative cos pi over 3, so negative half. So minus sine pi times negative half is equal to AB. So I've moved the 2 to the bottom because, look, the expression is slowly coming together, but because they want the 3 by itself, so I'm going to move the 2 to the bottom. So 2 times the entire expression, root 3 over 2 cos theta plus half sine theta. So I'm going to distribute 2 root 3 over 2, root 3 cos theta plus sine theta is equal to AB. And so we've shown that the length AB is equal to that. This is effectively the expression we want to optimize in terms of theta, because in B, what they're asking you is that given that AB has a minimum value, determine the value of theta for which it occurs. So I'm reiterating one more time. You want to optimize the length or the distance of AB in terms of theta. So you want to find the angle that optimizes it. So, hold on, yeah. So optimizing AB in terms of theta. So I've wrote the function because it's an expression or a function, which is 3 over root 3 cos theta plus sine theta. So now I'm differentiating AB with respect to theta. And this is where you're going to use quotient rule. So root 3 cos theta plus sine theta times the derivative of 3, which is 0, so this expression cancels out, minus 3 times the derivative of the denominator. So again, cos theta, derivative, sine theta, derivative sine theta, cos theta. Negative root 3 sine theta plus cos theta. So, and then on the denominator, root 3 cos theta plus sine theta squared. In optimization, 8 times out of 10 do not expand the denominator. It's not useful. Because when you did if you've done the curve sketching unit, you'll notice that the critical numbers for the denominator are not particularly useful, because either they will just not follow the domain or they have no value. The only time where the denominator is particularly important is in asymptotes, but that's a curve sketching thing. So we've simplified 3 root 3 sine theta minus 3 cos theta, and we find the expression of the derivative. Now we want to find the maximum. Because this is a first derivative equation, we're going to set it to 0, because that corresponds to the local extrema on f at x. So we're going to set dAb over d theta to 0. We're going to disregard the denominator. So 3 root 3 sine theta minus 3 cos theta is equal to 0. Now, we're solving a trig equation, and this is where sometimes you are like these techniques like factoring, trig equations, logarithmic properties, sine properties, you need to be very good at just doing these quickly, because these are ultimately tools and skills. Now, in the units themselves, like trigonometry, those are like fundamental skills that you have to do and know how to do to solve problems. So, but in this one, it's more or less a tool. So you need to be comfortable in doing these, and quickly especially. So we're solving for theta. So we're going to move 3 cos theta to the right. Typically, we don't move stuff in trigonometric identities because we don't want to lose solutions, but because you're not going to be crossing out things from the left and right, you should be safe and not lose any solutions. So 3 root 3 sine theta is equal to 3 cos theta. We're going to leverage the tan theta by dividing cos theta by cos theta, and then sine theta over cos theta, cancel out the 3 and 3. So we're left with root 3 tan theta, and then tan theta is equivalent to root 3 over 3, or 1 over root 3. And again, the angle. You should know straight off the bat that the theta is equal to pi over 3. So the value of theta, which is pi over 3, is the value for which AB will have a minimum value. Hopefully the video is going well so far, and as you can see, there's quite a lot of maths here. We're going to do one more question, but I'm not going to fully solve it, but I'm going to just show you, because I think this is the peak difficulty in terms of, I guess, a trigonometric focus. So here it goes. Actually, I'll take my words back. I don't think it's the hardest, but it's definitely close. I think if you can get this question, you definitely have a pretty good understanding and an abstract understanding of optimization. The key to optimization in general is you want to have a lot of training data. So you want to be exposed to different types of problems so you know their tricks, and you want to do them, like, I think minimum 2 times. I think if you do it 3 times, you'll definitely know the trick and you'll be very comfortable with it. And so the key to this is just being exposed to different types of problems. You're going to get frustrated that, oh my god, each problem has a new approach. But I think over time, you just know the approach and you just connect the dots and just kind of figure it out from there. And yeah, to be honest, that is the trick to optimization, as for things like related rates as well. So yeah. So the question is saying that consider the triangle PQR where QPR is equal to 30 degrees. Notice that they've used degrees this time. PQ is equal to x plus 2 centimeters, and PR is equal to 5 minus x squared cm. And they've given you the domain where x is in between negative 2 and 5, which makes sense because you can't have 0 lengths or negative lengths. And I'm going to just solve A for you because I think the rest are interesting. Also recall that this question is paper 2. And so you're going to have to use the graphing calculator, especially when you solve the roots. So that's where the graphing calculator skills are going to be pretty important, keeping that in mind. This wasn't the focus of the video, but you should be comfortable with using your graphing calculator. So it's saying that show that the area of the triangle is given by A is equal to 1 over 4 times x cubed minus 8x squared plus 5x plus 50. So again, I'm going to give you the hint for part A. I'm giving you the diagram. PQR, QPR angle 30 degrees. PQ, x plus 2, PR, 5 minus x squared. So you don't know QR. I'm not sure if it's relevant or not. But anyways, so again, we're going to leverage the area because remember, the area of a triangle, there's many ways of doing it. Base times height over 2. Counting the squares if you're given like a grid. But in this one, you can just multiply half times the lengths, QR, PR, and the angle between, which is 30 degrees. So sine 30. So half times x plus 2 times 5 minus x squared sine 30. Sine 30 is half. So 1 over 4 times x plus 2 times 5 minus x squared. Now notice that they gave the whole long expression, which means that you're probably going to have to expand those two terms, those two factors to get that expression. Because you have to show, right? And you have to show each step to get those reasoning marks. And then for the final mark, like the final thing is something called AG, which is answer given. So 1 over 4 times, I'm going to first expand the 5 minus x squared. Again, being comfortable with perfect squares. 5 squared, 25. 5 times negative 1x, negative 5x times 2, negative 10x. Negative x times to the power of 2, x squared. 1 over 4 times x plus 2 times 25 minus 10x plus x squared. And then you're going to distribute. So 25x minus 10x squared plus x cubed plus 50. And then minus 20x plus 2x squared. And then you'd simplify, so x cubed, like terms, so negative 10x plus 2x squared minus 8x squared plus 5x plus 50. And that matches the expression they've given you. Hopefully, actually, before I say that, look at the rest of the questions, try to do them. And to give you another one, this one is on, hold on if I can find it. Wait, hold on. Give me 1 second. Oh, I think I had it. Hold on. Okay, wait, I can't find it anymore. So I apologize for that slight delay. But hopefully this video has helped and given you a fairly good, I think, approach to optimization. I think it was recommended that you had some knowledge of optimization prior to doing these questions, and it also gave you more exposure to how the IB typically will test you on optimization. Pretty different from all the typical ones where they won't get out, like typical ones like regular programs won't give you the diagram, but then to compensate for that, they will give a much easier question. But whereas in IB, they'll give you a longer and relatively harder question, and they'll provide you the diagram because that's IB is trying to test your ability to optimize, to use your graphing calculator, and to understand the connection between the first derivative, second derivative, and the original graph. That's what they're trying to test you on rather than, I think, designing diagrams, which I find also equally important when you're doing things like engineering and whatnot. But anyways, that's beside the point. Hopefully this video has helped, and please be sure to like and subscribe to IB45 or Gone.